Hi. So we said that when an electron will move from, say, E1, which is a lower energy state, right, to E2, it will move to E2, which is a higher energy state. So here energy would be absorbed. Right now, since it has moved to a higher energy state is an unstable energy state. So it will move back to its ground state, to lower energy state. When it will move to lower energy state, it will emit energy, or it will emit radiation of frequency nu. Right? So the amount of energy that is absorbed or emitted, right, when an electron will transition from one energy level to another energy level would be equal to, we know that E is equals to h nu, right? We already know this, which is the energy associated with this quanta, right? Let me just quickly rub this. So when an electron will move from one energy level, right, to another energy level, it will release energy which is equal to the difference in energy of the two orbits, right? We'll just understand that. It's simple concept. So we said, suppose this is your nucleus, right, and this is your energy level E1, and this is your energy level E2, right, and this is your electron. When electron will move to higher energy level, right, it will absorb energy, right, which is equal to the difference in energy between these two orbits. Right, since it has moved to a higher energy level, which is E2, now it is in unstable state. So it has to, or it will immediately move back to its ground state, which is the lower state. It will move back. So here, when it will move to a higher energy state, or when it will do transition to a higher energy state, energy is absorbed. Here, when it will move back to the ground state, energy would be emitted, right? So this energy absorbed or emitted when electron will transition from one energy level to another energy level would be given by E2 minus E1 is equals to h nu, right? This is your Bohr relation of frequency. That's what we call it, right? This is known as the frequency of radiation. How we can define this as the frequency of radiation absorbed or emitted when transition occurs between two stationary states, right? These are two stationary states that differ in energy by delta E, which is equal to E2 minus E1, right? So frequency of radiation would be E2 minus E1 upon h, right? This expression is known as Bohr's frequency rule. Right? We can also write this as nu is equals to E2 minus E1 upon h. Right? Delta E, which is the energy difference between the two stationary states, h. This is known as Bohr's frequency rule. This expression nu is equals to delta E upon h, this is known as Bohr's frequency rule. Right, this is your Bohr's frequency rule. Now we have already talked about angular momentum, right? So the stationary states for electrons, I will just repeat, we have already discussed that the stationary states for electrons are n is equals to 1, 2, 3, 4 as we keep moving away from the nucleus, right? The integral numbers And like I told you in the beginning, that these n is equals to 1, 2, 3 that we are saying, right? N is equals to 1, 2, 3 would be called as principal quantum numbers. We'll see this in another video lecture when we'll do quantum numbers, right? This is your principal quantum number. And we have already understood the concept of negative energy, right? Why this energy, which is E is equals to minus 1312 upon n square joules, right? Kilojoules per mole. Why this energy is negative, right? We have discussed this, that what we have taken is that the energy when n is equals to infinity, E infinity, energy where at n is equals to infinity is 0, right? So when electron will come close to the nucleus, attraction between electron and nucleus will increase, right? When there is attractive interaction, that means energy would be released. When energy would be released from an electron which is already which is already 0, so its energy will become negative, right? So this model of atom is important, right? Remember the drawbacks so that you can easily understand the Bohr model of atom. And we have talked about the transition, right? Transition of electron from higher energy level to lower and from lower to higher. And this is the expression which we call it as Bohr frequency rule. When electron moves from higher to lower or from lower to higher, it will emit or absorb energy, right, which is equal to the difference in energy of these orbits. And when it will transition from higher energy level to lower energy level, it will emit radiation of frequency nu, which is given by this relation, right? And this fact, that when an electron jumps from this higher energy level E2 to lower energy level, right? When it jumps back to the lower energy level, it will emit radiation of frequency nu, right? And this explains for the line spectra of elements, right? And this energy emission is not continuous. Remember, this energy emission is not continuous, but this energy emission is in the form of small packets of energy which we call as photons or quantas, right? Emit radiation in the form of photons, right, or quanta, which are small packets of energy. And when you look at if this is this is your photographic plate where you are receiving the spectra of elements, these are the kind of lines that you see. These are lines. This is not a continuous spectrum, right? Its continuous spectrum is somewhat like this. When you have this no gap, continuous spectrum is no gap. But here you see that you have gap. You have gap because this line spectra, right? That is this is what we are looking for, the explanation for line spectra of elements. You have lines in the spectra of elements, right? Because energy is emitted, right, in the form of packets, right? So these lines correspond to these emitted packets of energy, right? That is why you get lines in the spectra of elements. It is not a continuous spectra because the emission of radiation is not continuous. Here in this case, the emission is not continuous. This emission is not continuous, but is discontinuous in the form of packets of energy, right? And due to which line spectra is observed, right? Basically, line spectra is observed when electron will transition from higher energy level to lower energy level, and on transition from higher to lower energy level, it will emit radiation in the form of packets, and these lines correspond to the emitted radiation that is in the form of packet or emitted radiation discontinuously, right? So this explains for the line spectra. So Bohr model of atom explained the line spectra. It explained the distribution of electrons in stationary states, right? And it explained the stability of, let's talk about the stability of atom, because Bohr model said that if this is your nucleus, right, then electron, right, electron is moving in this is the ground state. If this is the ground state, right, this is the ground state, means lowest energy state. So it will keep moving in this lowest energy state, right, and it will not radiate energy, right? It will not radiate any energy because it does not have any orbit below it. The ground state does not have any orbit below it, right? So it will not fall below the lowest orbit, right? And it will keep moving in this orbit without radiating energy, right? It does not, this electron in the lowest ground state will keep revolving without radiating energy. Since it is not radiating energy, so it will not fall into the nucleus, right? Since it does not have any orbit below it, so it will not fall in the nucleus or in any orbit below it, because there is no orbit. So since this electron is moving, right, in this lowest orbit, right, without radiating energy, right, since it is not radiating energy, so it will not move or it will not fall into the nucleus. This explains for the stability of atom, because what Bohr said, that electrons will keep moving in the permitted orbits, right, without radiating energy. It will keep moving in those stationary orbits, or the orbits that have stationary energy, right? So it will keep moving in this stationary orbit without radiating energy, hence will not fall into the nucleus. It explains for the stability of atom, right? So I hope this is clear. So you may get some numericals on things related to the energy of electrons and the momentum, right? The expression that we learnt in momentum, which is mvr is equals to nh upon 2 pi, right? Just remember all that, right? So I hope all this is clear to you, right? Now in the next video lecture, we will go through the drawbacks of Bohr's model, and then we will learn about the fine structure of hydrogen atom, right? So thanks. I hope all this is clear to you. Thanks.